Welcome to one of the most awesome editions of Comet Algebra ever produced. This video is for Chapter 11, Section 5, entitled Sum and Difference Identities. So as we continue working down the pink sheet proving these identities, we just have sum and difference and double angle left, and those are the two we're going to cover in this section. Now, we did a worksheet in class together where we derived the sum and difference identities. It was an adventure. It was somewhat painful at times. It was very long, but we persevered, we worked through it together, and they have been proven. So now in this video, we want to learn how to use them. So these sum and difference identities, these are on your pink sheet. You have them. So I just rewrote them here. What I want to point out to you is this may sort of look like distribution to you. It may look like this is cosine alpha minus cosine beta, but that is not it at all. This is not distribution. It really is where you're adding these 2 degrees, and then you have to work with the rest of the identity. It's more complicated than, it is not cosine alpha minus sine beta. And like I said, we proved that in class. So just a note, this does not mean substitution. So in learning how to use them, first I want to just remind you of something that you already know. You already know how to find the exact value of angles that are on the blue sheet from the unit circle that we've worked with and we've proven with these special triangles. So the sine of 30, if you look at your blue sheet, it would be the y coordinate of the sine of the 30-degree angle, which is the 1/2. And the cosine of 30 would be the x coordinate, which is square root 3 over 2. So I want you to be able to pull those off the blue sheet very easily, or you could be able to set it up and find them if you needed to. And just to remind you, these are exact. This is not punching on your calculator cosine 30 and getting a decimal equivalent that has been rounded off. We are looking for exact values. So now what we can do with these sum and difference identities, it has expanded our capability to find the exact trig ratios with more angles. If we can take the angle we're given and write it as a sum or difference of known angles, then we can apply these identities. So let's look at an example of what that means, what that looks like. If we're asked to find the exact value of the cosine of 105, you notice right away that 105 is not an angle we have on the blue sheet. It's not one of the special triangles angles. So we look at the numbers that we do have on your blue sheet. We have 0, 30, 45, 60, 90, 120, and so on. If we can use those degrees, those angles, and write 105 as a sum or a difference of those angles, then we can move forward. Now there's probably many different ways to come up with 105, but I just happened to notice that 60 degrees plus 45 degrees does add up to 105. So that's the one that I'm choosing to work with. Like I said, there's ways to subtract and get 105, and if you come up with a different combination, totally fine. So now after we get this, we look at our pink sheet and we follow the identity of cosine alpha plus beta. And then we enter the 60 and the 45 in there. So cosine of alpha plus beta says we have the cosine of alpha, which in this case is 60, cosine 60 times, now it says cosine beta, which is my 45, and then there's a minus sign. So remember, I'm just following the identity that looks like this, cosine of alpha plus beta, and I'm just entering in my 60 and 45. And now I have to subtract from that sine of alpha, which is sine 60, times sine beta, which is sine of 45. Now these are numbers. Now we substitute in the numbers. The cosine, looking at our blue sheet, cosine of 60 is 1/2 times cosine 45 is square root 2 over 2. Put your subtract sign in. Sine of 60, again, from the blue sheet, is square root 3 over 2. And the sine of 45, square root 2 over 2. So now just multiplying these two fractions, I get square root 2 over 4. Over here, recall that you can multiply numbers under the same radical. 2 times 3 is 6. Square root 6 over 4. And then the simplified, these are common denominators. So square root 2 minus square root 6 over 4. This is the exact value of the cosine of 105. This is not rounded off, it's not an estimation, it's the exact value. So some new things now that come into play with verifying these identities is now we have some actual degrees and we can substitute in these values. So I hope when you look at this, what I want you to see is that this is a difference identity. This is the cosine of alpha minus beta. And so we need to take this pi over 2 and put it in for the alpha. This x degrees, we don't know what it is, and we'll put it in for beta. So on your pink sheet, follow the first sum and difference identity, which is cosine alpha minus beta. So this gives us cosine of pi over 2 times cosine x, and then there's a plus sign, and then I have sine of pi over 2 times the sine of x. Now looking at your blue sheet, I don't know if you recognized pi over 2 is 90 degrees, and the cosine of 90 is 0, so we put that in right here. So I have 0 times cosine x plus, now we look up the sine of 90, and that is 1 times the sine of x. Anything times 0 is 0. 1 times sine is sine. So I have verified this identity. I got sine x equals sine x. Sometimes they'll give us the angle in radians, and you have a choice. You can stay in radians, look at the blue sheet and find two known angles that either add or subtract to get this, or if you prefer, you can switch this into degrees, completely your choice. I think, well, maybe I could look at it both ways. If you wanted to multiply this to degrees, of course we want the pi's to cancel, so we multiply by 180 over pi. The pi's cancel, and if I multiply 11 times 180 and I divide by 12, then I get 165. So this is the same thing as finding the sine of 165 degrees. So looking at the blue sheet again, there's a lot of different ways to add or subtract to get this, but the first one that I happened to see was that 165 is 120 plus 45. So now I need to look at the pink sheet and look at the sine of alpha plus beta and follow that identity, which would be the sine of 120 times cosine 45 plus cosine 120 times sine 45. And then going to the blue sheet and finding these values. All right, the last thing on our pink sheet that we need to prove at the bottom there is the double angle identities. And these are very easy compared to how we had to prove the sum and difference identities. So we're going to start with the fact that the cosine of 2 alpha equals the cosine of alpha plus alpha. And now I'm going to use the sum identity, I'm going to follow the cosine of the alpha plus beta identity, but in this case, both alpha and beta are the same, so we'll just use alpha. So this equals cosine alpha times cosine alpha, and then there's a minus sign, sine alpha times sine alpha. And if I go ahead and multiply these, I get cosine squared alpha minus sine squared alpha. And I'll just write this again. So this is the cosine of 2 alpha. And this is the first double angle identity. So we've just proved the first one. Now, on the pink sheet, this is given to us in 3 different ways, and this is very, very useful to have the 3 ways. So now we're going to start with that first one that we just proven, and we're going to do some steps, and we're going to prove the second one. So if you notice, this cosine squared, we can make a substitution using the first Pythagorean identity. If you subtract a sine squared from both sides, that means that cosine squared would equal, I'll put it in parentheses here, 1 minus sine squared. And then I still have this one, minus sine squared alpha. And if I have, now I have minus 1 sine squared alpha minus another sine squared alpha, that is 2 of them. So this is the second double angle identity. So now that's been proven. Remember, all these are equal to cosine of 2 alpha. So now that third one on the list with the cosine of 2 alpha, I would need to go back to this step up here, this first one, and make a different substitution. So to get the third one now, I would substitute in for this sine squared, going back to the first Pythagorean identity, and I need to subtract a cosine squared from both sides, and then I would get that sine squared right here, this sine squared, is equal to 1 minus cosine squared. So let's remember, we're going back to this step here, and now we're rewriting. We're going to keep the first cosine squared alpha, and then we're going to substitute in the 1 minus cosine squared. And once again, if I distribute the negative sign, I'll change that to plus, minus, plus. If I have 1 cosine squared alpha plus another cosine squared, whoops, I made an x, let's make that an alpha, I end up with 2 cosine squared alpha minus 1. And that one is the third one on the list of double angle identities. So now we have proven all of them on the pink sheet. Now we can use all of them in our work. So these are the double angle identities. These are from the bottom of your pink sheet. And now we're just going to do a couple examples to learn how to use them. These can be used to find the sine or cosine of an angle that's twice the size of any of the known angles on our blue sheet. All right, in this last set of examples, we're going to be asked to find the cosine of the angle, the cosine of twice the angle, and the sine of twice the angle. So of course, for B and C here, we're going to be using those double angle identities. However, for part A here, they just want us to find the cosine. So we're going to ask ourselves a question. If we have the sine and we want the cosine, the numerical value of it, how do we find it? Using the identities. So if you'll notice, of course, the Pythagorean identity of sine squared plus cosine squared is 1. This should bring you back to your days using the Pythagorean theorem when you know two sides of a triangle and you're asked to find the third side. We know this one, we know this side, its sine, and we know this side, the hypotenuse is 1. So of course, if we have these two known values, we can use them to find this unknown value. So let's plug it in, just like you did in the old days with the Pythagorean theorem. Now we'll talk about this piece of information here in just a moment. In the directions it said that angle A was in quadrant 2. That seems like a kind of small, insignificant detail, and yet it's very needed here in just a moment. So let's plug these in, just like you did with the Pythagorean theorem, and let's see if we can find the cosine. So the sine is 5/13, so we have to square that, plus cosine squared of A equals 1. So we need to square this fraction and subtract it from 1. So I have 1 minus 25 over 169. So if I change 1, so we have common denominators. 1 is 169 over itself minus 25 over 169. And I subtract that, I get 144 over 169. So now I have cosine squared equals this fraction. So to solve this for just cosine, I need to take the square root of both sides. And this worked out kind of nice because these are both perfect squares. But we run into an issue. The square root would give us a plus minus value. Plus minus 12 over 13. Well, we can't have two answers for the cosine of A. So we have to decide, is it the plus or is it the minus? And the way you determine that is you go back and look at what quadrant you're in. So if we look at any angle in quadrant 2, we notice that the x or the cosine is negative. So you have to actually select this. You have to select then that the cosine of A is the negative value of this fraction. So it's negative 12/13. So that becomes my final answer. And again, we knew that because we were told it's a quadrant 2 angle. So now moving on, we're asked to find the cosine of 2a. So look at what we want. We want to find the cosine, and the known information we have, I'm just going to write it here again. We were given up here that the sine is 5/13. So I'm just going to write that here. Sine is 5/13. So if I know the sine and I want to find the cosine, just scan down those three double angle identities and we want to choose the one that's going to bring us to what we want. So if we have sine and we want cosine, that looks to me like we should use the second one. I'll just write it here to refer to. So the cosine of 2a would be 1 minus 2 times the sine squared of a. Well, we have 5/13, so let's plug that in. 1 minus 2 times 5/13 squared. So then if we do the math here, square that, times it by 2, we get 1 minus 50 over 169. Again, common denominators and subtract. I get 119 over 169. And this is the cosine of 2a. So I'm done. Now they want us to find the sine of 2a. So that would involve that double angle identity that's written there to the right on your pink sheet. It says sine of 2, I'm just putting in a for alpha, equals 2 sine a times cosine a. Well, I want this, so I have the sine is 5/13, but I need to get this. Well, if we look back at our previous work, right up here in part A, we did find the cosine of A. The cosine of A is negative 12/13. So we're going to need to use that in our work down here. So we're going to put the negative 12/13 in for the cosine of A. And we already know that the sine of A is 5/13. And we need to multiply that by 2. I guess I kind of worked backwards there to get the sine of 2A. So if I do my multiplying right, 5 times 12 is 60 times 2, we have a negative, is negative 120. And 13 times 13 is 169. I don't think that reduces, so that is my sine of 2A. And so that's how we use these double angle identities. So now we've completed the pink sheet. You are free to use all of these identities in your work for the assignment for section 11.5. So have fun and God bless.